Good day, everyone. Welcome to chapter 29. So, we will be diving into the fascinating world of electromagnetic induction. So, this lecture is based on the 14th edition of University Physics by Yang and Fredman. And I am your lecturer for today's discussion. My name is Charmy Remigio. But before anything else, let me introduce to you our learning goals for chapter 29. First is how Faraday's law relates the induced EMF in a loop to the change in magnetic flux through the loop. Second is to how to determine the direction of an induced EMF. Third is how a changing magnetic flux generates a circulating electric field. Fourth is the four fundamental equations that completely describe both electricity and magnetism. And lastly is the remarkable electric and magnetic properties of superconductors. So let's start with a familiar scenario. So using a card reader at a gas station. So why do we need to swipe the card quickly? So the answer lies in electromagnetic induction. So we'll see how energy conversion relies on this principle and how Faraday's and Lenz's law explain induced current. So finally, we'll see how Maxwell equations provide a comprehensive framework for understanding electric and magnetic fields. So, in the 1830s, several pioneering experiments with magnetically induced EMF were carried out. So, here we see a simple setup. So, a coil of wire is connected to a galvanometer. So, when a magnet is stationary, notice that the galvanometer shows no current. So, this is our baseline. So now let's introduce motion. So as we move the magnet towards or away from the coil, the galvanometer registers a current. Importantly, this current is present only while the magnet is in motion. This current is what we call an induced current, and the electromotive force driving it is the induced EMF. So here, using the two-coil setup of the previous slide, we keep both coils stationary and vary the current in the second coil by opening and closing the switch. So the induced current in the first coil is present only while the current in the second coil is changing. Consider a coil placed in a magnetic field. If the magnetic field is constant and the coil's shape, location, and orientation remain unchanged, no current is induced. However, if any of these factors change, the magnetic field strength, the coil's shape, its position, or its orientation, a current will be induced. To understand electromagnetic induction quantitatively, we need to define a magnetic flux. So we can divide any surface into small elements of area dA. The magnetic flux through each element is defined as the component of the magnetic field perpendicular to the area B perp multiplied by dA. The magnetic flux through a flat area depends on its orientation relative to the magnetic field. So the maximum flux occurs when the surface is faced on the field. In this case, the magnetic flux is simply the product of the magnetic field, strength B and area A. So if the surface is tilted at an angle relative to magnetic field, the magnetic flux is reduced, and it's now given by dA times the cosine of the angle. So the flux is between 0 and dA depending on the angle. Finally, when the surface is edged on the magnetic field, the angle is 90 degrees and the magnetic flux through the surface is zero. This is because there is no component of the magnetic field passing through the area. And now we come to Faraday's law, the cornerstone of the electromagnetic induction. It states that when the magnetic flux through a closed loop changes with time, an induced EMF is generated. Mathematically, the induced EMF is equal to negative of the time rate of change of the magnetic flux. So d theta b over dt. So remember that the unit of magnetic flux is Weber, and 1 Weber per second is equal to 1 volt. So to determine the direction of the induced EMF, let's consider a scenario where the magnetic field is increasing. If the flux is positive and becoming more positive, so the induced EMF is negative. Conversely, if the magnetic field is decreasing, the flux is still positive, but becoming less positive. In this case, the induced EMF is positive. Now, let's consider a situation where the magnetic field is in opposite direction and increasing. So the flux is negative and becoming more negative. So the induced EMF is still positive. Finally, if the magnetic field is in the opposite direction and decreasing, the flux is negative but becoming less negative. So consequently, the induced EMF is negative. In practical applications like commercial alternators, we often use a coil with multiple loops of wire. So the induced EMF is significantly larger in a coil because each loop contributes to the total EMF. So if a coil has n identical turns and the flux varies at the same rate through each turn, so the total EMF is simply n times the EMF of a single loop. Lenz's law provides a convenient way to determine the direction of the induced current or EMF. So it states that the direction of any magnetic induction effect is such as to oppose the cause of the effect. So for instance, if we have a uniform magnetic field uniform magnetic field through a coil and the field is increasing. So the induced current will create a magnetic field that opposes these increases. So let's visualize Lenz's law with a magnet and a loop of wire. So on the left, as the magnet moves closer, the downward magnetic flux increases. So the induced current creates its own magnetic field pointing upwards to opposite this change. So on the right side, as the magnet moves away, the upward flux decreases. So now the induced current creates a magnetic field pointing towards pointing upwards to try and maintain the original flux. So here are the two more scenarios. So on the left side, the magnet is moving upwards, decreasing the downward flux. So the induced current creates a magnetic field pointing downwards to compensate. While on the right side, the magnet moves downwards, increasing the upward flux. So the induced current then generates a magnetic field pointing downwards to counteract this increase. And now, let's consider motional AMF. So, when a conducting rod moves perpendicularly through a uniform magnetic field, a motional AMF is induced. So, this AMF arises because the magnetic force on the moving charges in the rod separates them. So, it creates an electric field. So the magnitude of this AMF is given by VBL. So where V is the velocity, B is the magnetic field strength, and L is the length of the rod. So changing magnetic fields can also create electric fields. Imagine a long solenoid encircled by a conducting loop. If the current in the solenoid changes, the magnetic flux through the loop changes. So this changing flux induces an electric field within the loop, which is what drives the current. So this relationship is described by the equation shown relating the line integral of the electric field to the rate of the change of magnetic flux. So a practical application of induced current is found in eddy currents. When a piece of metal moves through a magnetic field or experiences a changing of magnetic field, circulating currents called eddy currents. So these currents are induced within the metal. So these currents dissipate energy and can be used for various purposes, such as in metal detectors at airport security. So the metal detector senses the eddy currents induced in any metallic objects the person is carrying. And now let's address a limitation of Ampere's law. So consider a capacitor being charged. If we apply Ampere's law to a loop around the wire leading to the capacitor, we encounter a problem. So it depends on the surface we choose. We either include the current in the wire or we don't. So it leads to a contradiction. So this suggests that Ampere's law, as original formulated, is incomplete. So to resolve this issue, Maxwell introduced the concept of displacement current. So as a capacitor charges, the electric field between the plate is changing. So Maxwell proposed that this changing electric field acts as a current, so which he termed displacement current. So this displacement current is proportional to the rate of change of electric flux between the plates, and it serves as the source of the magnetic field in the region. So all the knowledge we have discussed so far can be summarized into four equations. The famous Maxwell equations. The first equations is Gauss law for electric fields, which relates the electric flux through a closed surface to the enclosed charge. The second equation is Gauss' law for magnetic fields, which states that the magnetic flux through any closed surface is always zero. So the third Maxwell equation is Faraday's law of induction, which we've covered extensively. So it relates that induced AMF to the changing magnetic flux. The fourth equation is Ampere's law, is now complete with the addition of displacement current. So this equation relates the magnetic field around a closed loop to both the conduction current and displacement current passing through the loop. So in the empty space where there are no charges or currents, Maxwell equations take on the particular elegant form. So the first two equations become identical and stating that electric and magnetic flux through any closed surface are zero, while the third and fourth equations reveal a beautiful symmetry. It is a changing magnetic flux creates an electric field, and a changing electric flux creates a magnetic field. So this symmetry is fundamental to the nature of electromagnetic waves. So when a superconductor is cooled below its critical temperature, it loses all electrical resistance. So for any superconducting material, the critical temperature changes when material is placed in an externally produced magnetic field. So This shown is the independence for Mercury. So as the external field magnitude increases, the superconducting transition occurs at the lower and the lower temperature. So let's shift gears and discuss superconductivity. So when certain materials like mercury are cooled below critical temperature Tc, they exhibit a remarkable property. So they lose all electrical resistance. This critical temperature is not fixed. It changes when the material is placed in the or is placed in an external magnetic field. So as the external field increases, the superconducting transition occurs at a lower temperature. So this relationship is illustrated in the graph. One of the most striking properties of superconductors is the Misner's effect. So if we place superconducting material in a magnetic field and then cool it below its critical temperature, the superconductor expels all the magnetic flux from its interior. So this expulsion is called the Misner's effect, and it demonstrates that superconductors is not just a perfect conductor, it's also a perfect diamagnet. So here is an example of numerical problem. So a square coil of side 30 centimeter with 500 turns is kept in a uniform magnetic field of 0, 0.4 Tesla. The plane of the coil is inclined at an angle of 30 to the field. Calculate the magnetic flux through the coil where answer is 9 WV. So here is the solution where it comes from the formula of magnetic flux is equal to NBA cos angle is equal where the given n is equal to 500 times 0.4 we're given is p times 0.3 where it converts from 30 cm to meter times cos 60 angle is equal to 500 times 0.4 times 0.9 times 1 half is equal to 9 WP. So that is the solution of the problem. So example number 2 is a circular antenna of area 3 meters squared is installed at a place in Madura. So the plane of the area of antenna is inclined at 47 degree with the direction of Earth's magnetic field. So if the magnitude of Earth's field at the base is 40773.9 and we find the magnetic flux linked with the antenna. So as our given, P is equal to 4.40773.9 NT, while our angle is 90 degrees and our area is 3 meter per square. So these are the solution of our problem, where the answer here is 89.47 times 10 to the power of negative 6 WB.